I worked on a project, NASA 5000 Years Solar Eclipse Enhanced Catalog. My name is Parsha Abhinitri Koti. So, what is solar eclipse? Solar eclipse occurs when the moon blocks the sun's view from Earth either partially or completely. Introduction of this project. Solar eclipses have always fascinated people because they are rare events where the moon passes between the sun and the earth, casting a shadow on our planet. They make us curious about how universe works. NASA, the space agency, has been working on a project called NASA 5000 Years Solar Eclipse Enhanced Catalog. This project is a big effort to collect and study information about solar eclipses that has been recorded over the past 5000 years ago and continuing it. In this report, we will dwell into why NASA is doing this project, what they hope to learn, and how they are doing it, and what they've discovered so far from looking at all the historical eclipse data. So, problem statement and hypothesis. Why? Well, like, what are the points that we want to show in the project? Hypothesis 1 is solar eclipses with higher eclipse magnitudes are more likely to be of the total or annular type rather than partial or penumbral. This hypothesis suggests that eclipses with greater magnitude, indicating a large portion of the sun covered by the moon, are more likely to result in total or annual eclipses, which are visually more striking and significant. Hypothesis 2. There is a correlation between eclipse visibility and geographical hemisphere. This hypothesis proposes that the visibility of solar eclipses varies between the northern and southern hemispheres due to factors such as geographic location, atmospheric conditions, and Earth's tilt. It suggests that certain regions may experience more frequent or clearer views of solar eclipses compared to others. Hypothesis 3. The frequency of solar eclipses exhibits temporal patterns over the sample data period. This hypothesis suggests that the occurrence of solar eclipses follows cyclic or periodic trends over time, which are influenced by factors such as celestial mechanics, orbital dynamics, and Earth's axial tilt. It proposes that certain years may experience higher or lower numbers of solar eclipses compared to others, reflecting underlying temporal patterns in eclipse occurrences. So, the main motivation of this project is solar eclipses have fascinated people for a long time because they're cool and they tell us a lot about how the universe works. But looking at the old records of eclipses is tricky because they come from different places and times, like old books and new scientific studies. These records are important because they teach us how different cultures saw eclipses and how they fit into history. Because but because the records are so different, it's hard to put them all together and understand what they mean. So scientists need to use smart techniques like visualizations and work with different experts to make sense and create a create a clear and beautiful data out of it. Approach. I have used several approaches for creating the visualizations. First is the data collection. I got a bunch of old information about solar eclipses from Kaggle. Second is data pre-processing. Clean up the information to make it easier to understand. This involves making it fixing mistakes and organizing things in a standard way and removing all the unnecessary data from the data set, and also look for the missing values and replace the missing values with 0 or the median value. Third is the hypothesis development. I came up with ideas to test using the data. These ideas help us figure out if there were any interesting patterns or connections in the information. And fourth is the visualizations. I made pictures of the data to help us see what was going on. These pictures included things like graphs and charts that made it easier to understand the information. Next is the hypothesis 1. This graph shows how strong or intense different types of solar eclipses are. I have used box plot for this hypothesis. Total eclipses, where the moon completely covers the sun, have the highest intensity, while partial eclipses, where only part of the sun, have lower intensity. Other type of eclipses fall in between these two extremes. The graph uses a box plot to compare the intensity of each eclipse type. The x-axis shows the different type of eclipses, while the y-axis shows their intensity. The boxes show the range of intensity for each type of eclipse, with the middle line indicating the average intensity. This helps us see how intensity varies across different eclipse types. The colors and layout of the graph make it easy to understand and compare the intensity of different eclipse types. Next is the hypothesis 2. This graph shows where solar eclipses were visible across different parts of the world. The bars represent different regions with colors indicating the whether eclipse was visible or not. Most regions had the eclipse not visible, shown by the red bars. However, some places like Singapore and Rio de Janeiro has visible eclipses shown by the colored bars. The graph helps us see how visibility varies depending on the geographic location, with some areas not experiencing the eclipse while others do not. Hypothesis 3. This graph shows how many solar eclipses occur each year over a certain period. Each bar represents a year, and the height of the bar shows how many eclipses happened in that year. The different colors represent the number of eclipses per year, with orange indicating 2 eclipses, yellow for 3 eclipses, and red for 4 eclipses. This graph helps us see if there are any patterns or trends in the frequency of solar eclipses over the time. Additional visualization. I have used count plots. These four graphs show different aspects of solar eclipses. The first graph shows how often different types of eclipses occur, like total, annular, hybrid, or partial. The second graph looks at when eclipses happen in a year based on the remainder when divided by a certain number. It seems like more eclipses happen when the remainder is 0 or 5. The third graph shows the time between consecutive eclipses. It looks like most eclipses are about 18 or 29 days apart. The last graph shows how many eclipses happen in each decade. It seems like the number of eclipses is pretty evenly spread out across different decades. These graphs use different colors to make it easier to understand the differences between the categories being compared. They help us understand when and how often solar eclipses happen in different ways. Next is the correlation matrix. The correlation matrix is like a map that shows how different things are related to each other. In this case, it's showing how different factors related to solar eclipses are connected. The darker color shows how stronger relationships are. Dark red means two things are very different from each other, while dark blue means how they are very similar. The diagonal line shows each factor's relationship with itself, which is always perfect because something is always exactly the same as itself. Some factors like catalog number and delta t seem to go together a lot, while others like eclipse latitude don't seem to have much connected to each other. Overall, this map helps us see which factors might be important while studying solar eclipses and how they are connected to each other. Next is the scatter plot. The scatter plot shows how two things delta t and eclipse magnitude are related to each other for different types of solar eclipses. Each dot represents a solar eclipse and its position on the graph tells us its delta t, how long the eclipse lasts, and the eclipse magnitude, that is how much of the sun is covered. There isn't a straight line that connects the two dots, but we can see that eclipse magnitude gets bigger, delta t tends to get smaller. The different shapes and colors of the dots tell us which type of eclipse each one is, like the total, annular, or partial. Overall, the scatter plot helps us see if there is any pattern between how long an eclipse lasts and how big it is, and if different types of eclipses behave differently in this regard. Future scope, integration of advanced statistical modeling and algorithms to enhance prediction accuracy of the solar eclipse occurrences and characteristics. Talking to experts in astronomy like stars, sun, and the moon to refine analysis and interpret historical eclipse data and make people ready for the all eclipses. Conclusion. In summary, our project on NASA 5000 years solar eclipse enhanced catalog has been a significant effort to gather, clean, and analyze historical solar eclipse data spanning thousands of years. Through this work, I've gained valuable insights into the patterns, trends, and cultural importance of solar eclipses over time. The visualizations have vividly depicted the variety of eclipse phenomena and their distribution across geography and time. I've also highlighted the importance of collaboration and advanced analysis techniques in uncovering new knowledge about the universe. Looking ahead, there are exciting opportunities to further explore solar and lunar dynamics using advanced modeling and collaboration with experts in the field. Ultimately, our goal is to continue expanding our understanding of the cosmos and inspiring wonder of the future generations. Thank you.